ever really thought about the physics of heat? I mean, it's this invisible energy that's just flowing all around us, all the time. It connects the stove in your kitchen to the sweat on your skin after a run. Today, we're going to go on a little journey to really understand that flow. I mean, it's something we've all seen, right? But the physics behind it is just fascinating. This one simple question gets right to the heart of how different materials handle heat. And that is exactly what we are going to unpack. So, the answer really comes down to a property that you can think of as a material's thirst for heat. Yeah, seriously. Some materials are just incredibly thirsty. They can soak up tons and tons of energy without their temperature changing all that much. Others, well, they heat up in a flash. Okay, so the official sciencey term for that thirst is specific heat capacity. It's a super fundamental concept. It basically just quantifies exactly how much energy, say, a kilogram of a substance needs to absorb to raise its temperature by 1 single degree. This one number, it unlocks everything. And what's really cool is how elegantly this little equation lays it all out. Q over here, that's the heat we're adding. It makes sense that it's related to the mass, m, and how much we want the temperature to change. That's delta T. But the real magic ingredient is S. That's our specific heat capacity, that unique thirst number for every single material. So, what's the number for water? It is a massive 4,200 joules per kilogram per degree Celsius. Now, just for comparison, the specific heat of aluminum is only about 900. This perfectly explains why it takes forever to boil that pot of water. It has a huge thirst for heat. And, this exact property is why our oceans are so good at regulating the entire planet's climate. Pretty amazing. Okay, so we've got a handle on how materials absorb heat. But what happens when you put a hot object right next to a cold one? Well, it's not a battle. It's more like a carefully balanced exchange of energy. This is one of those fundamental laws of thermodynamics. It's simple, it's direct, and it is always true. Energy just naturally flows from hot to cold, never the other way around. The hot thing cools down and the cold thing warms up, every time. So here's the really crucial point. It's a perfect balance. The amount of heat lost by the hot object is exactly equal to the amount of heat gained by the cold one, as long as, no energy escapes to the surroundings. This whole exchange keeps going until they both reach the exact same temperature, a state we call equilibrium. So how do physicists actually measure this? They use a device called a calorimeter. It's basically just a very well-insulated container. It's designed to create a closed system, trapping all the heat inside, so we can accurately measure that perfect exchange. Heat loss equals heat gain. All right, now for a really fascinating twist. What if you keep adding heat to something, but its temperature doesn't change at all? I know, it sounds impossible, right? But it happens every single time you melt an ice cube or boil a pot of water. There's a hidden energy cost. This hidden energy is called latent heat. The word latent actually means hidden, and that's perfect. It's the energy a substance absorbs, not to get hotter, but to literally break the bonds holding its molecules together so it can change its state, from solid to liquid or liquid to gas. Let's just follow the journey of water for a second. First, you heat some ice up to 0 degrees. Then you have to add a whole bunch of latent heat just to melt it, all while it stays at 0 degrees. Then you heat the water all the way up to 100. And finally, you have to pump in a huge amount of latent heat to turn it into steam, all while the temperature is totally locked in at 100 degrees Celsius. And just look at these numbers. To melt 1 kilogram of ice takes over 300,000 joules. But to boil that same kilogram of water into steam? Whoa, it takes a staggering 2.2 million joules. This hidden energy of vaporization is just immense, and it has some absolutely incredible real-world effects. Okay, so now that we have these powerful principles, specific heat, and this great energy exchange, we can use them as tools. So let's put them to the test by solving a classic physics problem. So here's our setup. We've got a hot aluminum block, and we're dropping it into some cool water inside one of those calorimeters. We know the masses, we know the temperatures. The goal here is to use what we've learned to find that special property, the specific heat capacity for aluminum. Okay, first things first, let's just follow the flow of energy. We know heat moves from hot to cold. So the object losing heat is obviously the 100-degree aluminum block. That's one side of our equation, sorted. And who's on the receiving end of all that energy? The cool 15-degree water for sure. But we also have to remember that the calorimeter itself is going to absorb some of that heat.
So these two together make up the other side of our equation, the heat gain side.
And here it is, the crucial step. We just said heat lost equal to heat gained. We can plug in all the numbers we already know, and the only unknown left is S, the specific heat of aluminum. A little bit of algebra later, and our puzzle is solved.
Now, let's zoom out a bit and see how these principles show up in the world all around us. Because this is where the physics gets truly amazing.
You ever wonder why sweating actually works? It is latent heat in action. Your body pushes liquid sweat to your skin. To evaporate that sweat, to turn it into a gas, it needs energy. And it needs a lot of it. That huge latent heat of vaporization we just saw. And where does it get that energy? It steals it directly from your skin, which leaves you feeling cooler. So just how effective is this system? Well, the calculation shows that for an 80-kilogram person to cool their entire body down by 1 degree Celsius, they only need to evaporate about 14 grams of water. That is an incredibly efficient biological cooling system, and it's all thanks to physics. Okay, let's end with a big one, a real mind bender. Imagine you could convert the energy of a fall, that's gravitational potential energy, perfectly into heat. How high up would you need to drop a block of ice so that the energy from the impact is exactly enough to melt it completely? You know, this is just a perfect example of energy conversion. The potential energy from the fall, MGH, has to equal the latent heat needed to melt the ice, MLF. And what's really neat is that the mass, m, is on both sides, so it just cancels out. When you solve for the height, you get a truly astonishing answer, 33,600 meters. That is more than 3 times the height of Mount Everest. And really, that's the ultimate takeaway here. From a falling block of ice, to a burning stove, to the warmth of your own body, the energy is all connected. It's never created or destroyed, it just flows and transforms, connecting absolutely everything in our universe.
Thank you for watching my video. Please like, subscribe and hit the bell icon.